Hi, welcome to Arithmetic Series. What's the difference between a series and a sequence? We just did sequences and we've got the same sort of diagrams here, so they're pretty closely related. But what we're going to do now is to say, well, do we want to know not only the numbers here, what was it? 1, 3, 5, etc. That's the sequence. But maybe you might want to know the total number of dots in all of them added up. So you might be looking at 1 plus 3 plus 5 plus da-da-da-da-da-da. And this could be an infinite sequence. But when you want to add them, we call this a series. So that's the difference. A series is talking about the summation of the individual terms in the arithmetic sequence. So we're about the addition of terms here. And of course, in this little podium example from before, we might want to, if we were building this, what's the total number of bricks that we would be needing to build this? And the total number of bricks would be 1 plus 2. Each row goes up by 1. And that could be a practical question. Total number of bricks. So this again, when we write the terms there, the arithmetic terms with an addition, it becomes an arithmetic series. So the difference is, a series is about finding the total of the terms, still related in that same way, that the nth term is the one that came before plus a common difference. Something like that, or just remember an is, I've done it again, haven't I? Going back to a terms instead of mu, is a1 plus n minus 1d. But in better IB notation, we would use, as in the information booklet, mu n is mu n take 1. And down here we'd have mu's again as well. So mu n is mu 1 plus n minus 1d. So the relationship of each individual term is the same, but now we want to add them up. Let's go and have a look at, first, before we do try to add them up in the arithmetic case, let's have a look at some symbols that we use for addition in mathematics. So here's Pearson's, again I'm using clippings from Pearson's textbook for the new IB course, first examined in 2014. And there's their statement where we're looking at, in a series, we're looking at the sum, and the sum of terms, we call the sum a series. So there we have it written there. Sn is the first term plus the second term right up to the nth term. Just remembering, don't get fooled by this, n take 1 as a subscript means the term before the nth term, because it's got n take 1 as a subscript there. Okay, let's go down to the sigma notation I was speaking of before. The sigma notation is something that's used in mathematics quite a bit to mean the sum of. So most of the series we're talking about are infinite series. They can keep going. We might stop it at a certain point, but generally they keep going. And so we might talk about just adding up a certain first k of them, something like this, a1, a2, up to the kth term. That's called a partial sum, because you're not adding up all the terms. It could go on forever. It could be infinite. So there is a notation. Here it is here. Okay, commonly used in mathematics, not just in series work. And let's read what that means down here. It means the sum of, so this sigma means the sum of all the terms that look like this, from I is 1, so that's a little symbol, so the first one is A1, up to K, A2. So you're going to change this little subscript in there, labelling each one as A1, A2, etc. Let's come back up here. And so next one would be A3, right the way. And where does it stop? It says it stops at AK. So AK would be there. And the one before it would be AK take 1. So that's a symbol that we can use instead of all this here. Okay, so it represents the sum. And why sigma? Why that? Because this is the Greek capital for S, and so letter sigma, S for sigma, S for sum. So they are equivalent, and therefore we can use that quite logically to mean the sum of the terms. So we could use this one down here, saying we were summing from I equals 1 to I equals m to n. So that would be am, and keep going, add them up, m, and then this would be m plus 1 up to an. So we can put anything in here, the limits of that subscript, telling us where to start it and where to end it. Okay, so here we call m the lower limit and n the upper limit. We're saying how many terms of that type are we going to look at. Well, come on down then and let's have a look at the sigma notation. This is part of the work in sequences and series to understand the sigma notation. So let's try to unpack this first one here. This says the sum from I equals 1 to 5 of terms of the form I to the 4th. So let's do 1 to the 4th. I, there it is in there, and we start at 1, then we put I is 2 in, I is 3, I is 4, up to 5, because it says add them from I equals 1 to 5. What about this one? This says terms of the form 3 to the R, and you're allowed to start at R is 3 and go to R is 7. So 3 to the first one, 3 to the 3, 3 to the 4th, 3 to 5, 3 to 6, 3 to 7. Notice how you have an upper and lower limit. The lower is R is 3, and you go up to R is 7. And it always uses R is a member of the set of positive reals here. Okay, so that's important to remember that, set of positive reals. All right, what about this last one? This looks complicated. Let's have a look in here. It's x, subscript j, p of x of j. So, well, we don't know what that means. Let's put the terms in as it is, as it states there. J can go from 1, so that would be x1, p of x1. This is actually a formula for expected values in probability. We'll see this later on. So the next one is x2 times p of x2, xn times p of xn. So it's just a substitution in of the lower value of j up to the higher one, remembering you're going up in integral values with this notation. So it's quite a handy way of summarising lots of terms to be added. Let's come down and look at some more. A couple here. Let's look at example 14. Sum from n equals 0 to 5. So let's look at what's the form of the term. It says 2 to the n. So if n is 0, it'd be 2 to the 0. Then you go 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. It stops there because n is 5. It's the biggest value. Do you get the idea? And in example 15 here. Well, this is a bit hard. They want us to write this in sigma notation. So we will need to find the pattern of the terms for a start. And it isn't an easy one. It's not a common difference or a common multiplier here. What do we notice? Well, Pearson's is helping us here. First of all, we notice the term on top, call it k, the one underneath each time is one more. So they're saying, why don't we call this k over k plus 1, picking up the idea that the denominator equals one more than the numerator. So this is a bit of a harder sequence to look at, or series to look at, because we're adding them up. And we also notice that the signs of the terms alternate. Okay, so it goes up to 99 over 100. The first term is just a positive. So how do you make a positive? Well, it'll have to be neg 1 to the k plus 1. So it's squared for the first term. Neg 1 to the k plus 1. Therefore, the first term, when you put in, let's say k is 1, this will be neg 1 squared, which is a positive. Then the next one will be neg 1 cubed, which is going to be a negative. So that produces the alternating signs going from positive to negative, etc. So what have we got? Here's our final answer. In K-land, k is going from 1 to 99. You've got to start with neg 1 to the k plus 1 because the first term is positive, and then you stick in the k's in these holes. So that's a complicated one to generate a set of terms like that. Okay, so study that. All we're really trying to do is understand this sigma, that idea, and how you can use successive values in any formula to represent the addition of them. Sigma means add them up. All right, so what properties have we got for the sigma notation? If we added from I equals 1 to 5 of terms of the nature 2, see there's no I in here, no I, so the term doesn't change. So the sum means they're all going to be 2's. So you've got 5 lots of 2, which is 10. And so in general, here's your first rule. If you're adding up constants from I equals 1 to n, it just comes to nk. Okay, so you don't actually have to write them all out. If we, for example, had 5 times I, now I is obviously varying because I is from 1 to 5. So the first time 5 times 1, 5 times 2, 5 times 3 times 5 times 4, etc. So it's the same as this. So therefore, you could write it as 5 times the sum from I equals 1 to I. Put the constant out the front, okay, because they've all got it in there. So here's the rule down here. If you have the sum from I equals 1 to n of ki, you can just add up all the i's and multiply by the constant out the front. Just a bit of a quicker way of doing it rather than writing out all the terms. And what's the last one here, I think? Suppose we're looking at the sum of 2 different ones in here, 2 functions. Okay, so you're putting in k is 1, so it's 1 squared plus 1 cubed. K is 2 squared plus 2 cubed, because that's what this is telling you to do. To create the term, you have to do those things to the k's. So then you go right up to n squared plus n cubed. But you could separate it, couldn't you, into the squareds and the cubes. So you could say it's the sum of the first part, the sum of the second. So the general rule is, if you're summing over the same interval, mind you, from 1 to n for both of them, you can split them up as 2 individual sums and do the 2 separately. That's a little bit of work with sigma notation. There's not a lot of that in this course, but you must be aware of being able to read it and understand how to generate the terms. All right, let's come down now and have a look at arithmetic series. We're looking at adding the terms, aren't we? That's the difference between a series and a sequence. We're looking at adding up all the terms. How are you going to do that? The first 50 terms, a partial sum. Let's say this keeps going, this arithmetic series here. So how could you do the first 50 terms? Well, let's write them out. Here they are. Right up to 248. And then you could turn it around the other way and start with the highest and go up to the lowest. So there's two ways of writing S50. Going up, ascending and descending. So if you then added these 2 up, you'd have 2 lots of S50. And what do you notice? They all come to 251. And that's because there's a common difference there all the time. So therefore, how many of them are there? There are 50. So it's 50 lots of 251 is 2S0. So S0 is 50 over 2 lots of 251. And that's a quickie way of doing that. Do you know the first person who ever did that method? He was a little guy at the time and a very important mathematician later on. His name was Gauss. And I think he was about 5 years old. And his maths teacher was really getting frustrated because Gauss could do lots of problems far more quickly than even the teacher could. So he said, well, I'll fix this little fellow. We'll tie him up with a bit of a problem. It'll take him a while to work out. So he said, look, Gauss, go away and add up all the whole numbers between 1 and 100. He smiled and he thought, that'll keep him busy for a while. And what did the young fella do? Well, he did just what we did then. He said, well, if that's the sum, then if I put it the other way round, this will be going down by 1 each time, right down to 1 there. So that's another way of writing the sum. And if I add them up, so that's S plus S will be 2S, I will get every time 101. All right, up to there, 101. So then he said, how many terms are there here? 1 to 100 is 100 terms. So 2S is 100 lots of 101. So 2S is, what is that? 101, 2 noughts on the end. So S is a half of that, 5050. So he proudly ran out to the teacher and said, look, I've done it. And of course the teacher was dismayed. He's back again. I've got to find more work for young Gauss. So that was the first time, it's called the Gaussian method, if you like, of doing that addition. An interesting system. Let's go and see if we can generalise it to see what it would look like for any term. Okay, so Pearson's here is using the term A1. We would like to use mu n and mu1. Remember, mu n equals mu1 plus n minus 1d, that sort of thing. Let's do it. Let's write Sn, the sum of n terms, so A1 plus A2 plus A3, right up to An. And how would we write that? That's A1 plus A1 plus D, then 2D, up to our general term. And therefore, we can say what? Well, let's actually turn them around here. So if we said adding the terms vertically up in this top row, these two top rows here, and doing them in reverse now. So here, an take D, going backwards. Okay, going backwards, take D away. So it's the highest term, and then the D less than that, and so on. And what do you notice when you add them? At the beginning here, you're going to put an addition here. So it's A1 plus AN. Then A1 plus D, AN take D, because we've worked it backwards, A1 plus AN. Hey, they're all going to come to A1 plus AN. Okay, because we've reversed the order of terms. So this one is in reverse order. This is going from the largest n back to n equals 1, or mu1 or A1. Okay, so what have we got? Well, we've got 2Sn as before, and how many terms? Got n terms, and they've all come to A1 plus AN. So if we divide by 2, we have that form there. So that is a nice way of generating a formula for the sum of n terms. We would normally say Sn equals n over 2 first term plus last term, and that's in the IBD information booklet for this course. Let's go down and work on it a bit. We can actually, let's say we didn't know the last term. you didn't know the 50th term, we might need to work that out. So we'd say mu n is mu1 plus n minus 1d. And if we did that, and we've done it over here with A1, so stick that in place of mu n, and we get this formula. This is probably more useful because it's saying all I need to know is the first term, A1 in this notation, or mu1, and the number of terms and the difference, and then I can put these numbers in there and work out the sum of any number of terms. The only disadvantage of this formula, come back up here, this formula here, is that you must know the last term. Well, often we don't. We know the first and the difference. We should then probably go and use this form to actually arrive at the total sum. All right, let's come down and do a look at a bit of a summary here. And so there are two forms for the sum of n terms of an arithmetic. There they are there. I want to refer to the IB information booklet, which is this one here, and unfortunately we made a little mistake here. This is from the geometric sequence. Okay, so that doesn't fit in there. What we should have is Sn equals n on 2 mu1 plus mu n, and Sn equals n on 2 mu1 plus n minus 1d. This we'll see later on is the sum for a geometric, as I've got there. So that shouldn't have been screen clipped in there, but what the IB has are this pair here in mu terms, not A terms. Let's see if we can use it now. So coming to example 16, find the partial sum for the first 50 terms. Why is it a partial sum? Because we're saying, we are indicating that this sequence would go on, this series would go on infinitely. ... We only want to go up to the first 50 terms. So let's write down the formula. The sum is n on 2 by 2 mu1 plus n minus 1 by d. Okay, let's put the numbers in. 50 terms divided by 2, 2 times the first term, n minus 1 times d, and there we have it. A very neat way of adding up all those terms. Okay, so that's our solution. Using the first formula requires that you know the nth term. So generally we wouldn't do that, because you've got to go through all the work to get the nth term and then add it up that way. So really, this is the most useful formula generally. Let's come down and have a look. Now, I've taken this from Pearson's. There's only, in exercise 3.4, there's only about half a dozen problems. There's only 2 on summing an arithmetic series. So you might pause the presentation, have a go. I've taken some screen clippings from another publication, Hayes and Harris. Their book on standard level sequence and series work. So we're going to do some of those in a minute. So have a go at these two. And so pause the presentation. And now come along with me and we'll look at the solutions. There are the solutions there. Put them all up there together. So that's fair enough, I think. Now, what I want to do is take you on a bit of a longer journey, more practice with arithmetic series. Come down now and have a look at a couple of examples from Hayes and Harris publications. So find the sum to 50 terms, same problem. They're using here the IB notation, which is good. What about the sum of this one? Mu1 is -6, the difference is adding 7, and they're saying, well, this time we know the last term. They're telling you sum it up until the terms come to 141. So we could actually use this one. Okay, you could work out that, the sum of well, you need that, but we could use this, and we've got to still work out n. How many terms are there? Okay, in this one. You're going to use this one because we know that and that. We still need to find n. So over here, we can say 141, we want to know its n value. So it's mu1 plus the d times n take 1. And we work out that it's the 22nd term. and then we can use that second formula. So they've both got their advantages and disadvantages. The difficulty with this formula is that you do need to know that n number to put it in front anyway. All right, so let's go and do some practice from Hayes then. And here are some problems for you. There's quite a few here, and you can see my brick problem down here. So that's good. So want you to have a go at these. I think there's a bit of sigma notation here, same sort of stuff. And you've got to unravel the information as it's given using mu1 equals mu n equals or whatever, and d equals. Try to list the information that you've got there first of all and work through them. All right, so there's the first 6. I'll come down here and we go down to 13 problems. So there's 7 through 13. And you can pause the presentation any time. And of course, I've got some answers, just the answers for you down there. So you might come back and have a go at these. All right, so quite clearly we're interested now in taking this another stage further and finding the sum of the terms in both an arithmetic or a geometric series. Have fun with that. There's just a couple of new ideas there. What we'll do next is go on to summing terms of a geometric series and see what you think. At the moment though, it's cheers from me. Catch you in the next presentation.